Docker is an important technology to guarantee that deployments are fast and consistent across different platforms and systems. Welcome to the Get into Cloud podcast. My name is Coin. Today we're talking about Docker. It's quite a big subject. We have a lot of ground to cover. I'm going to break it into a number of sections. We're going to talk a little bit about containers first. We're going to talk a little bit about Docker as a platform. We'll go into the images for Docker and containers. We'll talk a little bit about the Docker files and container configuration. We'll briefly talk about Docker Compose and what it's used for. Go a little bit over the container registry, and finally talk about next steps. So a conversation about Docker really is going to start with a discussion about containers. Container technology has been around really quite a long time. It was baked into Linux for a number of years. It's been around a long time, but only recently popularized through the efforts of Docker. Containerization is effectively a way to package applications and their dependencies in an isolated environment. This isolation ensures that the application can run consistently across various computing environments, from development to testing to production, and across multiple clouds and other systems as well. It should be obvious that the advantage of containers is portability. If it can run anywhere, then that means you have a lot of flexibility on where you can run these environments. Because you're packaging your dependencies in with the application itself, you get a lot of consistency and efficiency as you deploy to new environments, go from dev to test to prod, or as you deploy in other platforms. This is especially good for cloud, particularly because they deploy so fast. They're able to deploy in an auto-scaling type pattern, which is great for elastic environments like cloud. They're very resource efficient because they share the host OS kernel across all the containers with the host itself, so they're very quick to start and stop. So it might be helpful to take a little bit of a walk down memory lane. If you recall, in the early days, you had individual physical servers, and your applications would run on those. This was very wasteful, as you can imagine, because the app owners in the business would often buy more server than they needed just in case. They did not want to buy a server to run their application and then find that the application ran very poorly. So they would often purchase much more server capacity than they needed, and those servers would largely be idle. It's also true that the application companies, like if you were purchasing a particular application, buying it off the shelf to run in your data center, the application companies would also publish what they would say would be the minimum specs for those servers to run. And because the companies aren't bearing cost for those servers, they would often tune up the specs, the minimum specs for their software, so that the software always performed well. There was really no negative from their perspective to over-tuning the specs on a physical server. So you often had very expensive servers running software and mostly idle almost all day, sitting at 1% CPU utilization, barely using any of the RAM that was purchased. Then along comes VMware, and VMware is a virtualization technology. Right, so the idea is to trick a server into thinking that it is a physical server by mimicking all of the communication that would typically happen between the operating system and the physical hardware. And so the concept of virtualization is to say it virtualized those physical pieces. The application thinks it's running on a real server, and the server itself thinks it's also a real physical server. So it thinks it has disks, it thinks it has power supplies and CPUs and things like that. And those VM images were a huge step up from having physical systems. You could put hundreds of VMs on a single physical server and see a lot of efficiency and save a lot of money. But those VMs were still quite large, and they were full operating system images, and they would have all the same drivers and the same kind of installed pieces that a server might have. So it was still a a much weightier proposition. Certainly better than a physical server, but still very heavy implementation of virtualization. And so the next step up is to go to what's called a container. And a container doesn't think it's in its own server. A container is in fact sharing the operating system's kernel across multiple containers on the host. So containers really only have a portion of the kernel inside of their container image, and then really just the running code that sits on top. In many cases, they don't have very much disk space at all. Unless you're mounting a disk, they only have minimal temporary space. They have a slice of the CPU, they have a slice of the RAM, and so they boot very, very fast, and they're very light. And the container operating system lacks a number of the drivers that the host would have, and just doesn't implement much of the software that a core operating system would need to implement. And so in that space, it makes them much more secure, because if there is a vulnerability in some sort of host driver software, a VM image would have that vulnerability and a container would not. Now, the host server that the container sits on would likely have that vulnerability, but it's much easier to patch one underlying core system than it is to potentially patch hundreds of systems that might have that vulnerability. So lots of advantages to using containers, and that is the kind of the concept of containers at a high level. So Docker itself is a platform for developing and shipping and running those applications inside of containers. And as I mentioned before, containers have been around a long time in Linux, but Docker really helped to popularize them by making a piece of software that made it easy to package an application and its dependencies into a single portable unit called a Docker image. And then this image can be shared and distributed and run across different environments. Docker empowers developers and system admins to create and manage those containers on their local machine, making it easy to replicate that runtime environment during the development process and then push that into the upstream environments as well, your dev, your test, and prod. And this answers an age-old problem that developers would work on their own system. They are working on a laptop or a computer. They are writing code on their laptop and their computer, and oftentimes that code would work on their system. And as soon as you moved it into a server in a data center, the code would fail. And there was this battle of it works on my machine. The classic kind of meme is it works on my machine. And so a lot of development hours and operational hours are spent trying to address this problem where a developer is developing in an environment that's not similar to the environment in which the code is going to run. And Docker basically solves that by shipping the developer's machine, because it's all self-contained inside of the container. So yeah, at a high level, Docker is primarily focused on packaging and running those containers. Docker images are created and stored and run using that Docker engine. It's probably important here to mention that Docker is different than Kubernetes. So you often hear about those two talked about as if they are the same thing. So it's important to maybe draw a little bit of a delineation. So Docker, the engine and its software, is mostly, as I mentioned, concerned with the management of the Docker container, how to define the Docker container, how to ship the images that are created, how to manage those images in containers as well. Docker Swarm is an orchestration engine that's used for running multiple containers together and orchestrating how those containers are born and die and how they interact with other systems. Docker Swarm is similar to Kubernetes, and Kubernetes is an orchestration engine that's intended to allow you to run very sophisticated and clustered systems. Run those containers, you run Docker containers on top of Kubernetes, and then use Kubernetes to organize and orchestrate how they're going to be spun up and spun down, how they'll be allowed to communicate with each other, how disk will be shared and allocated to those containers as well. And so Docker Swarm is more akin to Kubernetes, and Docker is more akin to container definition, container image creation, and container registries, which we'll talk about a little more in a minute. One thing to understand about Docker images and containers is that they are read-only templates. They contain the application, they contain its dependencies, and containers are instances of Docker images that can run as isolated process. So they can run on your machine, they can run in Kubernetes, they can run in ECS, in AWS, in the cloud, or in other places. All right, so let's talk about Docker files and container configuration. So the Docker file is the name for the file that Docker looks for to configure a Docker image, configure a container. So Docker files are text files. They're usually just called Docker file, which is not surprising. That it defines how the image should be built and what should be included. Docker makes it super easy to build these images and to build on top of existing images. So I'll talk a little bit about the registry more in a second, but one thing you need to understand is that because these are read-only, every image is going to be built on top of another image. So you're going to start with a base image and you'll build on top of that. So in your Docker file, you will have some basic commands that you can use to create a Docker image, to create a container. And the very basic one that is almost always first is the from command. And the from command indicates the image that you're going to be building on top of, because you're going to be creating a new read-only template and you start from a base image. So you could use the from command to pull Ubuntu latest, the latest copy of Ubuntu. And Ubuntu has already pushed a pre-made Docker image into the registry for you to use. You could take a copy of Alpine Linux and take the latest version or a particular version. You could put the version number at the end and align it with what Alpine has put into the registry for you to use. Or some application companies have published their versions of images as well that are kind of prefab and ready to use. So you could choose Nginx, latest, and you would get the latest and greatest Nginx container that comes kind of pre-configured for you to use. You would go look at how they're defining the image and what their recommendation for how you use that image is, and you would follow their pattern if you took their pre-made image. You wouldn't need to, though. You don't have to. You could choose to start from Ubuntu and then install Nginx on top with a set of commands that you could run. The second kind of key command I'm going to go through just three kind of basic commands, but the second command is copy. Copy allows you to copy files from your local system into your container image. And it's quite simply a way to push files into your image so that you don't have to manipulate files inside the image during the build process. So in the Nginx example, you might have an Nginx configuration file that you've created that has all of your specific Nginx configurations. And so you might start with a from command that pulls from Nginx latest. Then you might copy your Nginx config into the place where the Nginx team has said where it's going to be looking for Nginx configs. So your second command might just be a copy command. And then the third command is the command, CMD, and that tells the image what it should run when it's born. So if you have an Nginx container, it'll just run Nginx. So you can have command and then the command to run Nginx. You might feed in some other arguments along with your command. And there is an alternative. You can use entry point instead of command, and they're not quite the same, but the idea is, what is the point of this container? It should run what when it's born? And a container is always going to be running something. It's not like a server that you create and then you decide later what it's going to run. A container is going to be born running an application. If that application dies, the orchestration system will reboot the container. So that's one thing you'll notice. If you were to create a container to run Apache, and then you get onto the container and kill the Apache process, the container will go away. The container's point is to run a system, and so you have to tell it what it's going to run when it's full. Now, Docker Compose is an extension of the Docker language that allows you to configure multi-container applications and systems. It allows you to tie those containers together in kind of an infrastructure as code pattern that would allow you to connect containers together and to indicate what ports they might be listening on, how they might communicate with each other, and some other details. But effectively, it's a tool for defining multi-container applications in a single configuration file. So it's usually docker-compose.yaml. It's a YAML file, and you would list in your services and applications. I would encourage you to take a look at the Docker Compose option. I will say that in a lot of cloud roles, there are other ways to define how you want multiple containers in an application to be talking to each other other than Docker Compose. But Docker Compose is somewhat popular, and many of the orchestration engines understand the Docker Compose language and can consume it. So you should be at least a little bit familiar with Docker Compose, kind of the common things that you would expect to see in that, so that you can understand it better. All right, one of the last things I'll talk about is the container registry. And I've mentioned this before, Docker has its own registry, and every container is defined from a previous container. And so in the registry, you can see the various containers that are available. And many times this can save you a tremendous amount of time. As I mentioned in Nginx before, if you wanted to set up Nginx, you can find an existing Nginx image that would allow you to deploy Nginx in the click of a button from Nginx latest. And you have a container with Nginx running automatically. So then it becomes just a point of you looking at the details in the registry. So in the registry, you should be able to search for something like Nginx. You'll see the container and what the from command should be formatted as so that you can pull from Nginx. Then you'll see details of how they would recommend that you configure Nginx using whether you're going to copy in a config file or how you should approach that. And you'll see instructions for how to do that. And then there's also usually a link to their GitHub where they're publishing the commands that are running. So it can sometimes be very helpful to look and see, how did Nginx install Nginx on a basic container? In fact, you may want to know what is the underlying operating system as well. So you can go to that GitHub and see, in the Nginx container, are they calling from Ubuntu? Are they calling from Alpine? And so you can look at that information to see what is upstream from the container that you're working with. You can do searches to find all kinds of applications where images have been published to the registry and are available for you to consume. Of course, you're going to want to create your own images that have your application details baked in. You might have environment variables that you're pushing to the containers. You'll have application-specific configurations. So you're going to start from theirs and then layer yours on top. Then you want to save and publish your images to a registry. Now, you might not publish them to Docker because maybe you don't want them to be public. So there are lots of options for private container registries. In AWS, it's called the Elastic Container Registry, which is quite simple. Of course, Azure and GCP also have local container registries, which is great. And you can use those to save versioned copies of your application Docker container images and utilize those to have a point for saving those to push them into the environments. Also very helpful for rolling back. If you have published a new version of a container and you've started to roll that into your dev environment, you find that it is having issues, you roll back to the old container image and now you have a copy of the pre-existing code. So using a registry is an important part of if you think from a DevOps perspective, the entire CI/CD pipeline. If it is a container-based application, the pipeline is going to include pushing those files to a registry and saving them into some sort of private registry. Okay, so we've covered a lot with Docker. Let's talk about what you need to do for next steps. And I've talked a little bit about learning Docker Compose. I think that's important. You should look at Docker images and containers, understand how to create Docker files and kind of the key commands that are important for Docker files and building your own. Really, if you have a Mac or Windows, probably Linux as well, you can download Docker, the Docker engine, and install it locally on your machine. So this is a great way to enter in the world of Docker and start to get your hands dirty playing with Docker images, building Docker images, defining those images in Docker files, building those images locally on your machine, and running them locally on your machine. And so I would recommend installing and playing around with that, getting familiar with Docker files, getting familiar with Docker Compose as well, and then focus on doing projects that include containers, container images, and registries as a part of the process for the deployment. So you've heard in other episodes that I'm recommending that you get your hands dirty with this technology using projects and labs that encourage you to do hands-on work. Very important. You'll want to look for projects that include Docker, Docker images, image creation, Docker file manipulation, and the running of those images in an environment, whether that's a deployment to ECS or to Heroku or to another platform that might be free or available for you to explore and test with. But really, the next step here is to continue your learning on Docker, dive into Docker file creation, Docker image creation, dive in a little bit to Docker Compose, and then look for projects that can encourage the use of Docker and container technology so you can continue to learn and grow around this important technology. Thanks so much for listening to this episode of the Get Into Cloud podcast. I created this podcast to help people just like you who want to start and accelerate their cloud careers. Please take the time to like, subscribe, click, follow, do all the things on whatever platform that you use to listen to this podcast. We want to spread the word so that everyone can know that there's a pathway for them to get into cloud. Thanks so much for listening. Thanks for your help. Have a good day.